Systems of inequalities. First, let's talk about solutions to equations and inequalities. If we have a one variable equation, most often we're going to end up with a solution of just one value. If we have a one variable inequality, we're going to have more than one solution, but they're all going to share some characteristic, such as instead of x is equal to 5, it's all of the values where x is less than 5. Now, we practiced how to graph this, and this would be just one-dimensionally because we just have one variable. So x is less than 5. I would use the open bracket and then shade every value that is less than 5. Now we want to look at solutions two-dimensionally. So we're going to look at the xy axis, and we want to graph all of the ordered pairs A, B, such that A and B, when substituted into the original x and y, will give us a true inequality. So first step, and I'm going to start with y is less than 2x. The first step is to think about this as y is equal to 2x, and I want you to plot a few points on that line. So if I were going to graph y equals 2x, I would know that it goes through the origin, and that because it's plus 0, and that the slope is 2 over 1, so I can do up 2 over 1, up 2 over 1, or I can go down 2 to the left 1, and so forth. So we get an idea of what this is going to look like. Now, when we connect those dots, it has everything to do with whether this is an or equal to. So because it's a less than 2x, I'm going to connect these dots, but I'm going to connect it with a dashed line. So my line looks like this. Now I still haven't graphed the solution. The dotted line is just like when we used the open bracket, when we just graphed x is less than 5. That's what a dotted line tells us, is that all of the points on that line are not included in the solution, but all of the points up to that line are included. Finally, we are going to do step 2, which is do a test point in in each of the regions. Now, in this case, we have just one line, so think about this as region 1 and region 2. One of those regions needs to be shaded. And to figure that out, we're just going to use a test point. So let's use a test point of 3, 0. That's this point, 3, 0. Using 3, 0, that's 3 for x and 0 for y. So plugging it into this equation, 0 for y is less than 2 times x, 3 for x. So is 0 less than 6? Yes, 0 is less than 6. Therefore, this whole side should be shaded. Now, just to ensure that we understand, that means the other side shouldn't be shaded. So let's use another test point of, say, -2, 1. -2, 1 would be, I'm going to erase this work. -2, 1 would be y of 1 is less than 2 times -2. 1 is less than -4. That is false, so this side should not be shaded, and it confirms that we shaded the correct side. Now let's do the same for my second inequality. My second inequality is y is greater than or equal to 3. So first thing I do is think about it as y is equal to 3, and that would look like a line that goes through right here, and because it's or equal to, that's a solid line. Now, this one's pretty straightforward because I'm looking for all the y's that are greater than or equal to 3. So that's going to be the values here above 3. And again, if you're not sure, use a test point. So I could use a test point of say negative 2, 1 that I used before. Negative 2 for x, 1 for y. That says 1 is greater than or equal to 3, which is false. So that value shouldn't be shaded. So the opposite side of the line should be. Here are a couple of questions for you to try on your own. So press pause, sketch these inequalities, and when you're ready, press play to see how you did. So to begin, I gave you a fun parabola, a quadratic graph, but this one was pretty straightforward. If you weren't sure how to graph it, plug in points 0, 0, 1, 1, 2, 4, negative 1, 1, negative 2, 4. This is an or equal to, so this should be a nice solid line. And then we're either going to be shading inside the parabola or outside the parabola. So let's choose a test point of 0, 2. And you can choose any test point you want. So if you chose something different than me, that's just fine. This is the point 0, 2. So if this makes the equation true, I'm shading in between the parabola. Otherwise, I'm shading outside the parabola. So y, which is 2, is less than or equal to 0 squared. Is this true? Is 2 less than or equal to 0? And that is false. Because it's false, that means all of the area outside of the parabola should be shaded. For my second equation, I have y is greater than 4x minus 2. So again, I'm going to think about using slope-intercept form, that's negative 2. Using my slope of 4, so 1, 2, 3, 4 over 1. I'm just going to do those 2 points, and I'm going to connect this with a dotted line. And then you can use a test point. I also find, and be careful here, if you have the equation in slope-intercept form, I'm looking for any y that is greater than, so that tells me I'm going above the point of negative 2 because the y's that are greater than negative 2 are above it. If you have that in standard form, say you had 4x minus y is less than negative 2, or I'm sorry, less than positive 2. It's not always going to point in the right direction. So just be careful. Again, if you're not sure, plug in a point. Let's use the point 3, 0. Now, according to the way that I've already shaded, that should be false. So let's double check. 0 for y, 3 for x. That gives me 0 is greater than 12 minus 2, or 10. Is 0 greater than 10? No, so 3, 0 shouldn't be shaded. It should be shaded on the opposite side of the line. Let's take a look now at systems of inequalities. Just like a system of equations, where we had several equations, linear or otherwise, and we were looking for a point of intersection, for a system of inequalities, we are looking for a region where every inequality would be shaded. So to start, what we're going to do is we're going to just graph each of these lines. So I'm going to graph this one in blue. X minus y is less than 2. You can choose to turn that into slope-intercept form. I like standard form using the just cover-up method. So if I cover up x, I get negative y, and again, we're thinking about this as equals. Negative y is equal to 2, so y is equal to negative 2. And again, cover up minus y, so I get x is equal to 2. And that gives me 2 points, and that's all I need to be able to graph. So I'm going to use a dotted line to connect those. Now, to shade this, again, let's use a test point. I'm going to use 0, 0 as a test point. 0, 0 as a test point would give me 0 minus 0 is less than 2. 0 is less than 2, and that is true. So that's everything above the line. Now let's look at x is greater than 2. I'm going to use green. So x is greater than 2 would be right here. This is where x is equal to 2. Where are the x's greater than 2? Over here. And then finally, I'm looking for y is less than or equal to 3. So that's a nice solid line. And where are the y's less than? The y's less than are below. So what a mess, right? This isn't super fun. So what we're looking for is where do all of the shaded regions meet? So I'm going to get rid of the shading, just so we can kind of understand how to go about this. Typically what I do when I'm doing this by hand, and granted, we're not going to do it by hand very often. I am going to show you how to do this in Desmos. But if I looked at my original, let me change back to that color. If I looked at my original first equation, remember I said I was shading towards 0, 0. So I'm just going to put a little arrow to indicate that I'm shading above and to the left of that line. And then for x is greater than 2, I was looking to the right of that line. And for y is less than or equal to 3, I was looking below. So where is below the line and to the right, below the yellow line to the right of the green line and above and to the left of the blue line? That's this region right here. Now, because I have graphed it, I can certainly find those points because we also want to find the vertices of the region. And the vertices of the region would be 0, 0. Nope, just kidding. 2, 0. That's this point right here. 2, 0. And 2, 3, which is this point right here. And 5, 3. Mathematically, to find those points, if you didn't graph it and you were just looking for those points, you would have to solve 3 systems of equations, x minus y equals 2 and x equals 2. I would solve that to give me 2, comma, and then plug the 2 in. 2 minus y equals 2, so y is 0. That would give me the 2, 0 point. I would have x minus y equals 2, y equals 3. So obviously this is something comma 3. Plugging in 3, I get x minus 3 equals 2. I would add 3 to each side to get 5. That gives me this point. And then finally I would have x equals 2, y equals 3, which gives me the point 2, comma 3. So of course we can find all 3 of those points by solving smaller systems of equations. Now, I'm a math professor, so I am all for showing work, but when it comes to systems of inequalities, and in our next section, linear programming, we're going to find that being able to use technology is going to be beneficial for us. So if you'll notice, I have all 3 of my inequalities entered, but I don't have them graphed yet. So I just want to show you some things about Desmos. If I were to graph all 3 of the regions, I can see just by visual inspection that this does seem to be the correct value or the correct shaded region, which is the solution set to our system. Now, I'm going to show you a couple of things that I think will be helpful to you, not only when learning about graphing inequalities or systems of inequalities and linear programming, but for your final project in my course as well. So what I'm going to do is, before I try to shade only this region, which is the correct region, before I do that, I want to find the corners of that region. And this will come into play particularly when we have linear programming in the next section. So what I'm going to do is I'm going to create a table, and I'm just going to follow in order. So this point down here was 2, 0. And then I had the point 2, 3, and then I had the point 5, 3, and then I always go back to the original, because what I'm going to do is I'm just going to add a line there so that I know what the outside looks like. And you can have a solid line or you could have a dotted line. Now, what you can't do is have some solid, some dotted, which isn't great, but you get the idea. So I know that this is the region that I care about. I also know that I don't love all the shading that's going on. So what I'm going to do is I'm going to use my original equation, and I'm just going to use a restriction. I'm going to say x is greater than 2. Close that bracket. I'm going to say y is less than or equal to 3 and close that bracket, and then unshade those two. And voila, I now have exactly that shaded region. Let's take a look at one more of these by hand before we switch completely to Desmos. So to graph this system, I would have x plus y is equal to 5. Again, using that cover-up trick, I would say y is equal to 5. And cover-up trick, x is equal to 5. So I know that this equation is going to, the graph of this equation is going to be a dotted line that looks kind of like this. That wasn't my best work. And now I'm looking for a test point, so let's use 0, 0. 0 plus 0 is less than 5. That's true, so that's going to be shaded in this direction. Then we have y equals x. Y equals x is the line that looks like this. And again, it's going to be dotted. And let's use the point 2, 0. You can use any point that you want, as we know. So 2 for x, 0 for y. 0 is greater than 2. That's not true. So I'm not going to shade towards 2, 0. I'm going to shade on the opposite side of the line. And then we have x is greater than or equal to 0. So x is greater than or equal to 0 would look like this. Nope, that's the other one. Sorry about that. X is greater than or equal to 0 looks like this. And where the x is greater than 0, they are to this side. So it appears that this is my shaded region. And I'm looking for an intersection point. And this one seems pretty obvious to be 0, 0. And this one seems pretty obvious to be 0, 5. This one doesn't seem quite so obvious, so let's see where the green line and the yellow line meet. That's these two. So I'm going to say x plus y equals 5 and y equals x. So replacing, I could have y plus y equals 5, 2y equals 5, y equals 2.5, which means x, since x and y are the same, is also 2.5. So this point is 2.5, comma 2.5. Feel free to check your work in Desmos. Let's take a look at a couple of special cases, and we're just going to look in Desmos for that. So for the first, I'm going to look at x plus y is greater than 5 and x is less than negative y. This is obviously a special case because there would be no intersection point between those two regions. So this solution set would be the empty set. There is no point of intersection. There are no values that would make x plus y greater than 5 where x is less than negative y. The other special case is not a no solution question, but more of an infinitely many solutions, unbounded question. So we can see here that the area that would be shaded would be between these two values. So there's really only one vertex that defines the region, and the rest of the vertices, any other solutions, are just in an unbounded area, which means there's no endpoint that's going to continue forever in this direction. So that is the other special case. Now, why is it important to point that out? Because that will affect our solutions in our next section, 7.6. Up next, we have section 7.6, linear programming.